two-valued Boolean algebra. It is possible to formulate many Boolean algebra on the basis of elements we choose and the rules of operation. In this book, we will deal with only two-valued Boolean algebra. Why is it called two values? Because we only use two elements 0 and 1 with the binary operations and, or, and not, that is inversion. The following is the truth table and input 0, 0. So 0, 0 is 0, 0, 1 is 0, 1, 0 is 0 and 1, 1 is 0. So 0 means false and 1 means true. So if both the inputs are false, output is false. If 1 is false, 1 is true, output is false. 1 is true, 1 is false, output is false, and both are true, then output is true. So in case of AND, if both true, then true, otherwise it is false. In case of OR, if both are false, then false, otherwise true. So 0 and 1, 1, 1, 0, 1, 1, 1, 1. And in NOT, you take the complement. 0 becomes 1 and 1 becomes 0. We are now going to demonstrate that the Huntington postulates are valid for two-valued Boolean algebra. Let S equal to 0, 1 and the operators plus, dot and not. So closure. The closure is obvious from the table, which shows that the result of any operation is either 0 or it is either 1. So it belongs, 0, 1 belongs to S. Identity. From the table we can write 0 plus 0 equal to 0, 0 plus 1 equal to 1 plus 0, which is 1. 1 into 1 is 1, 1 into 0 is equal to 0 into 1 equal to 0. So you are also satisfying this. The commutative laws are A plus B equal to B plus A. So 0 plus 1 is 1, which is equal to 1 plus 0 is 1. 0 into 1, 0, which is also equal to 1 into 0. These laws can be satisfied due to symmetry of the table. This is illustrated from the following examples. So if the input is 0, then A into B is 0, B into A is also 0, A plus B is 0, B plus A is 0. 0 and 1, 0 into 1 is 0, 1 into 0 is 0, 1 plus 0 is 1 and 0 plus 1 is 1. If it is 1 and 0, then again the same thing, 0, 0, 1, 1. If both the inputs are 1 and 1, then A into B is 1, B into A is 1, A plus B is 1 and B plus A is 1. Next is distributive law. The distributive law of A dot B plus C is equal to A dot B plus A dot C can be proved by using the truth table. A is 0, B is 0, C is 0, B plus C is 0, A dot B plus C will be 0, AB 0, AC 0, AB plus AC is 0. So let's take one example from this table. A dot B plus C is equal to AC plus AB, AC plus AB. So suppose if the inputs are 0, 0, 1, then first what we do, B plus C will be 0 plus 1, that is 1. So you get A dot 1. What is A? A is 0. So 0 into 1 is 0. Now AC, A is 0, C is 1, 0, A is 0, B is 0. So answer is 0. And then you have a plus sign. So 0 plus 0 is 0. Here also you got a 0. Here also you got a 0. So LHS is equal to RHS. So like this we can prove for each and every element. We can also prove addition over multiplication. inverse from the table, it can be easily seen that A plus A inverse equal to 1. 0 plus 1 is 1, 1 plus 0 is 1, A into A inverse is 0, 0 into 1 is 0, 1 into 0 is 0. Postulate 6 says there exists at least two elements A and B such that A not equal to B. As the Boolean algebra has two distinct elements 0 and 1, this postulate is getting satisfied because 0 is not equal to 1. If A is 0, then B has to be 1. If A is 1, then B has to be 0. A and B can never be equal. Associative law. This law states that the order in which the logic operations are performed is not important because for any order the effect is same. If you do A into B into C or if you do A into B into C, that means you first solve this bracket then multiply it by C, or you first solve this bracket and then multiply by C. Answer is same. You first solve A plus B bracket then multiply it by C, or you first then add it by C, or you first solve B plus C bracket then added by A. Answer will be same. So let's take one example from the table. Let's take 1, 1, 1. So first I will do A into B into C. So A into B into C. A is 1, A into B is 1, into C is 1. 1 into 1 is 1. Again 1 into 1 is 1. So answer for this is coming 1, which is equal to A into B. A into B into C. So A is 1, B is 1, into 1. 1 into 1 is 1 into 1. That is also 1. So 1. So LHS is equal to RHS. So hence associative law is proved. You can similarly try for the addition also.